problem 22 from the review paper. In this problem, a satellite is in a circular orbit around some unknown planet. The satellite has a speed of 1.7 times 10 to the 4th meters per second, and the radius of the orbit is 5.25 times 10 to the 6th meters. A second satellite also has a circular orbit around this same planet. The orbit of the second satellite has a radius of 8.6 times 10 to the 6th meters. What is the orbital speed of the second satellite? So we're trying to figure out how fast the second satellite is going. Well, unfortunately, we can't find the speed of the second satellite without knowing the mass of the planet. That's important. We can't do anything without that. We have an equation for speed from our notes, but that equation requires this mass. So that's the first thing that we're going to do. We know a lot about the first satellite, so we're going to use the information we have about the first satellite to solve for the mass of that unknown planet. So in the first satellite, the force holding that in place around the unknown planet is the force of gravity. So we know the force of gravity must be the centripetal force. And our equation for gravity up in space is Newton's law of universal gravitation. So big G, mass of the satellite, multiplied by the mass of the planet, all divided by the radius of the first planet squared. That's going to equal mass of the satellite times the velocity of the satellite squared all over that radius. What we can do here is we can start canceling some things out. Mass of the satellite is in both sides. That can cancel. The radius is in the bottom, in the denominator of both, so that can cancel on the right side and the squared can cancel on the left. Now what we need to do is rearrange our equation for the mass of the unknown planet. So when we do that, we would get that the mass of the unknown planet is equal to the speed of the satellite squared multiplied by the radius of the satellite divided by the gravitational constant. From here we can plug in some numbers and solve. Our velocity is 1.7 times 10 to the 4th meters per second. And that radius is 5.25 times 10 to the 6th meters. And that's all over 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. When we plug all of that into our calculator, what we should get is that the planet has a mass of 2.27 times 10 to the 25th kilograms. With that information, we can solve for the speed of the second satellite. To do that, I'm going to move on to a new slide. So now for the second satellite, again, we know that the force of gravity has to be the centripetal force holding the satellite in place. Our equation for gravity is still big G. Now it's the mass of the second satellite times the mass of the planet divided by the radius squared. And that's going to equal mass of the second satellite times the speed of the second satellite squared all over the radius. Again, we're going to have some stuff that cancels. The mass of the satellite cancels out, and the r squared cancel out. So when we solve for the speed, we just have to do the square root of the left side, and that gives me the square root of the gravitational constant times the mass of the planet all over the orbital radius. That gives me the speed. Now all I have to do is plug in my numbers. Gravitational constant is, as always, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. We just solved for the mass of the planet, which was 2.27 times 10 to the 25th kilograms. It's all divided by the radius, which was given, and that is going to be 8.6 times 10 to the 6th meters. And when we plug all of that into our calculator, we should get that the speed is 13,282.5 meters per second. And that's the speed of the second satellite.